Using the method of contradiction, we will prove one more problem. So the question is the following: true or false? Determine the following statement is true or false. The statement is this: let A1, A2, etc. be infinite sets such that A1 contains, A2 contains, etc. That is, this is a decreasing sequence of sets. So the claim is the following: then intersection n equal to 1 to infinity, an is infinite. So we have to say first of all whether this statement is true or false, and after that we would like to justify the conclusion. So whatever we conclude from the statement, we need to justify that also. So in mathematics, when we try to prove something, if we want to prove that something is true, we have to propose rigorous mathematical arguments in such a way that those arguments will work for whatever A1, A2, etc. you are choosing, with the only condition that they are infinite and they are decreasing. But if we want to show that the statement that we are making is wrong, we need to just establish an example for which the assumption that the statement that we make is wrong. If you recall from one of the previous classes, we had actually constructed such a sequence of sets. We had taken the following sets: A1 equal to 1, 2, etc. A2 equal to 2, 3, etc. an in general equal to n plus 1, etc. Let us see if these an satisfy that condition, the assumption given in our statement. A1 is infinite, A2 is infinite, an is infinite, therefore all these sets are infinite sets. Now what about decreasing? A1 is consisting of 1, 2, etc. A2 starts from only 2, therefore A1 contains A2, A2 contains A3, etc. Therefore this sequence of sets A1, A2, etc. an is a decreasing sequence of infinite sets. Now what is that we have to check? We have to see whether the intersection of all these sets is infinite or not. But before establishing whether this set is infinite or not, we need to at least check that whether this set is going to be non-empty first of all. Let A equal to intersection n 1 to infinity a. To see if it's non-empty, we will try to take one element from this A. Let A belongs to A. First of all, we have to clearly say that if possible, because we don't know whether such an element exists or not. If A belongs to A, then A belongs to an for every n, because A belongs to capital A means that A is in the intersection, therefore A has to be in each and every set, therefore A belongs to an for every n. But what is the least element in an? An starts with n and goes on like that, therefore A has to be greater than or equal to n. If A is greater than or equal to n, if A is greater than or equal to n, if A is greater than or equal to n, A greater than or equal to n for all n implies that A is greater than or equal to A plus 1 also, because if A is a natural number, A plus 1 is a natural number, A is greater than or equal to n for every natural number, therefore A is going to be greater than or equal to A plus 1 also, but this is not possible. So this statement, this conclusion where we arrived at, this is wrong. This is a contradiction. But why did this contradiction happen? This is basically because we assume that an A exists in this intersection, therefore no such A can exist in that intersection, or the intersection A is equal to intersection n equal to 1 to infinity an is the empty set. Forget about being infinite, this has no elements at all. Therefore, if you are taking a decreasing sequence, then there is no guarantee that the intersection will be infinite, and in fact the intersection can be even empty. So our claim, our statement that we made is false. Therefore, the statement is false. In a previous session, we established the fact that the square root of 2 is not a rational number using the method of contradiction. We will see another example here in which we establish a fact related to the absolute value function using the method of contradiction. The statement that we want to verify is the following. Let A be a real number. So A is given and it is fixed. The claim is this: modulus of A is less than epsilon for all epsilon in R with epsilon greater than 0 if and only if A is 0. So in other words, what we are stating here is that modulus of a number is less than every positive number if and only if it is 0, or 0 is the only non-negative number which is less than every positive number. We have to prove two facts here. One is that if modulus of A is less than epsilon, for every positive epsilon we have to show that A is 0, and the other part is that if A is equal to 0, then modulus of A is less than epsilon. That part is obvious. So first part is this: we have to prove that if A equal to 0, then modulus of A less than epsilon for every epsilon real number, epsilon greater than 0. You know that in this case modulus of A is going to be just equal to 0, and epsilon is anyway given to be greater than 0. Therefore modulus of A has to be less than less than 0. That's obvious. The next part we have to prove is that let modulus of A less than epsilon for all epsilon greater than 0, epsilon real number. Now we have to show that A is going to be equal to 0. So to show that A is 0, we will assume that its negation is true. What is its negation? The negation of A is equal to 0 is that A is not equal to 0. So assume the negation of A equal to 0. That is, assume A to be non-zero. So if we assume A to be non-zero, there are two cases. A can be either a negative number or A can be a positive number. In either case, we know that modulus of A, by our definition, it's going to be, therefore modulus of A is positive. Let us write modulus of A to be equal to epsilon naught to be equal to modulus of A. Now epsilon naught is positive. By our assumption, whatever epsilon positive we choose, mod A has to be less than that epsilon. Therefore in particular modulus of A has to be less than epsilon naught, but modulus of A is already epsilon naught. Therefore epsilon naught less than epsilon naught. Hence we are arriving at a this actually gives rise to a contradiction. So why did this contradiction happen? Basically because we could find one epsilon naught satisfying this property. That is basically because we assume that modulus of A is greater than 0. So modulus of A has to be equal to, therefore modulus of A must be equal to 0. If modulus of A is equal to 0, then A must be equal to 0. So using the method of contradiction, we establish that if A is such that mod A is less than epsilon for every positive epsilon, then A must be equal to 0. There is no other way.